So he doesn't get his results for the
I think it's 8:15. Yeah.
Yeah.
All right. I will begin. Dear Father, we thank you for this day. I thank you again for this class and for these students. Help us to have a good class today. Help us to glorify you what we do learn. In your name I pray, Lord Jesus. Amen. Yes, once upon a time, if I had a test graded, I would give it back to the class at the start of class just because I couldn't help myself. But then I learned that my reward then as an instructor is for the next 75 minutes to be like peppered with questions about the test I don't want to talk about. So I'm going to resist the urge and violate your wills and wait until the end of class to give it back to you, because otherwise you'll be distracted. I mean, you're already distracted, but you'll be less distracted. Example 1. Let's look at another example of Lagrange multipliers. This one's a little different. I'm not certain I even have an example like this in my notes. But there's definitely an example like this in the recommended homework. So let's talk about it. Not this one exactly, but something like it. And I'm making this up. So since I'm just making this up, there's a good possibility that the Lagrange multiplier equations that we come across I won't be able to solve, but we're going to try. All right, so here goes. Suppose you've got an ellipsoid, all right, and you've got a plane, all right, and they intersect in some curve of intersection, right, like there. And let's suppose that that curve is given by the common solution set of, let's say, x squared plus 4y squared plus 9z squared equals to 1. And let's make the plane relatively simple. Let's do x plus y plus z equals to 1. So C is the intersection of those two surfaces, all right? So that's a curve in 3 dimensions, right? And then my question is simply this. Which point on this curve of intersection, let's say, is closest to this point over here? Let's make the point not too ugly. Let's say 1, 2, 3. That's not. I'll probably regret. Let's 1, 2, 0. 1, 2, 0 should make it friendlier. I don't want the algebra to be impossible here. Let me throw 0 into the mix. First of all, as we should with any question I just made up, we should check. Does the question make sense? Do we even need calculus to solve it, right? Because if that point 1, 2, 0 is actually on the curve of intersection, well, we're done, right? So is it on the curve of intersection? Well, 1 plus 2 is 3, so yay, it's not on the curve of intersection, all right? Okay. So again, the problem here, we're trying to minimize the distance from this curve of intersection, this point, let's say x, y, z, right? To this guy right here. We're trying to minimize this distance. But fundamental labor-saving, calculation-saving observation, if we minimize the squared distance, that will minimize the distance. So our objective function here would be what? What am I trying to minimize? Can you guys tell me? It's
4y squared plus 9z squared equals x plus y plus z.
But that would not be the, wait, what? No.
You should use x minus 1 squared.
Yeah, x minus 1 squared.
Times y minus 2.
Oh, nope, not that either. Nope. It's got nothing to do with the ellipsoid equation. This is the distance between this point and that point squared. So it's just the distance squared formula. Here it's just x minus 1 squared plus y minus 2 squared plus z squared. That's our objective, is to minimize that distance squared right there. Now, so this is not, the ones we did last time, we only had a single constraint function, right? Now we've got 2. But geometrically, the idea that we went through last time still makes sense. But here's how the Lagrange multiplier looks like in this case. What we're going to do is we're going to put nabla f actually equal to, say, lambda 1 I guess Stewart uses lambda and mu. If I use Stewart's notation, we'll have lambda, the gradient of G1, plus mu, the gradient of G2. And the reason for that is simply that we need the gradient of f to be in the normal space to the curve. Now, we haven't really talked about a normal space to the curve, but if you think about it, if a curve is going through 3 dimensions, right? You could talk about the normal to the curve, the normal space to the curve. Like, think about this. If I've got a curve like this, right? And the tangent vector is like this, where's the normal space? It's what? I mean, something like this, right? Or down here, it could be more like this, I don't know. Maybe do it over here. The point is the tangent vector to the curve, right, would be the normal to the normal space. So if we were using the Frenet frame, the normal space would be spanned by what? Like the normal vector and also the binormal. Like the normal and the binormal would be perpendicular vectors in the normal space to a curve at a point. So if you think about it, and you think about the derivation we did yesterday, this would be what we would say on the basis of that derivation. In this particular case, the gradient of f has to be built from the gradients of both of the constraint curves. So this is a little bit trickier because now we don't have just one Lagrange multiplier, we have 2, right? We have 2. But maybe we can still solve it. Let's see here, what's the gradient of f? It's 2 times x minus 1, 2 times y minus 2, 2z, right, is equal to what? Lambda times, what's the gradient of G1? I guess I need to tell you which one's G1 and G2. So that's, I'll let you choose, Violet. Which one's G1, which one's G2? Wait a minute, you're not Violet. What's happened? This isn't right. Are you Violet's sister? Rose? No, that's not Rose. Let's see here. So G2? Maybe, this is G1, right? This is G2 maybe? So G1 would have gradient what? 2x, 8y. Is it too early for my stupid jokes? 18z. And then plus mu, which is another Lagrange multiplier. And what's the gradient of G2? Well, that one's easier. 1, 1, 1, right? So is there any hope of solving this? Let's count the number of equations we're up against. What are we up against? Well, we're up against the 2 constraint equations, but also what? 2 times x minus 1 equals to, oh man, if I was smarter, I would have made that plain. Is it too late? Could I make a change to the problem ever so slightly to make the algebra like plausible? Yes, no? So what could make this example like way easier is just to erase this x. Like that. Which would then erase this. I think that's all. No, I think that'll make the algebra work out easier. I could be wrong. Let's work on it. So 2 times x minus 1 is equal to 2. You should set a timer. After 5 minutes, if we haven't made progress on this, we got to bail. 2 lambda x, and then 2 times y minus 2 is 8 lambda y, plus mu, and 2z is equal to 18 lambda z plus mu. So we've got those 3 equations, but we also have these 2 equations, right? How many equations is that? It's 5, right? 4 of them are linear, right? Also known as friendly. One of them's nonlinear, but it's only quadratic, so it's only partly unfriendly. Have you ever solved an algebra problem like this? Do you remember in college algebra when you solved algebra problems like this? I surely hope you don't, because if I assigned this problem to my college algebra class, there would be a revolt. There would be like a group of 20 of them that went to the dean's office en masse to demand my firing. You know, like, no, I would not do this to college algebra. And that's the beautiful thing about the calculus sequence. As you go on, you discover that while you thought you were a master of algebra, there's more out there you don't know how to do yet. Maybe this is that. So how can we solve this? I mean, we don't really care what the lambda and the mu are. Our goal is to eliminate those and to come up with equations that just isolates x, y, and z, right? Can anybody tell me how to do it?
Subtract everything from the equations, put everything on one side, then they're all equal to 0, so you have one huge string of equations. For one variable at a time in each equation, and then you have a smaller string of long equations.
But I want something lazier and quick. So I mean, I don't disagree with you. Putting everything equal to 0 and kind of just doing it that way, that's not a bad idea. But here's one thing. If I subtract these equations, I eliminate mu, right? So then I get 2y minus 2z minus 4 is equal to lambda times 8y minus 18z, yeah? That's a nice equation because it's got no mu in it. And then if you we can solve for lambda. See, lambda is equal to what? Well, lambda on the one hand is x minus 1 over x, right? See that from the top equation? X minus 1 over x. But on the other hand, it's also equal to what? From this equation right there, it's equal to, well, 2y minus 2z minus 4 divided by 8y minus 18z, which I think we can simplify a bit. That's actually what? Y minus z minus 2 divided by 4y minus 9z. Well, isn't that lovely? So now we have 3 equations and 3 unknowns. Hey, that's better than 5 equations and 5 unknowns, right? And they're just the three variables we actually want to solve for. X, Y, Z, right? So, all right, I guess next thing I would do is admit that I don't want to spend 20 minutes of class time solving this. My point is, this is how you'd set it up, and you could go from here. And if I had an hour, maybe I could solve it. And if I wanted to make the problem easier, what could I have done? What would make this problem radically easier would just simply have been, instead of erasing one of these, if I erased 2 of them, then things would have gotten much nicer, much faster, right? I could make this a problem that would be like not crazy to put on a test. It's like kind of the hard problem by simply instead of putting y plus z equal to 0, if I just put like y equal to 1, all of a sudden this algebra would become much easier. Okay? Yep.
You also have intersected this before doing the just curve.
Well, that's essentially what we're doing. So you're like, couldn't you just like restrict your attention to just the plane where everything's happening and make this a 2-dimensional problem?
Or like just the curve from where they intersect?
Well, yeah, I mean, that's what this math is doing. I mean, you're not wrong. But there's no like nice system of coordinates on that because the plane is tilted and junk. Now, there would be a nice system of coordinates if I had made my plane like y equals to 1. See, then it would have been in the xz plane. So you could have just used xz coordinates on the problem essentially, and it becomes a 2-dimensional problem, sort of. But the objective function is still kind of wonky because it's got the 3rd dimension in it, and somehow that has to figure into this story, which we'd only really appreciate if we worked that out. Listen, I have easier examples in the notes which I should show you. So let's do that. I don't think I have one like this in the notes though, so I wanted to just show it to you for a minute here. make sure I'm not projecting personal information here. Let's see, where are we? All right. So we worked that problem yesterday. This one I don't think we've worked yet. Well, we more or less worked this one last time, the closest point on the plane with different numbers. Here's another one. So I just want to talk through about 3 or 4 of these examples with you. Because, well, there's kind of an uber example at the end that I need to go through with you, because that example actually is like the logical basis for our later analysis. So it would be good for us to actually look at that together. But on the other hand, you don't want me to spend an hour of class to derive it either. So that's where these slides come into play sometimes. This one here, we're looking at the function, if I'm a laser. Here we're looking at the objective function e to the xy. And I want to find the extrema of it on the curve x cubed plus y cubed equal to 16. Now, do you remember what that looks like from Calculus 2? Well, neither do I, right? Because that's not a standard curve. But it looks something like this. Whee! Thank you, Wolfram Alpha. Of course, any number of graphical softwares could do that for you. But if we look at the g of xy equal to x cubed plus y cubed, let's say equal to 16, then I set gradient of f equal to lambda times the gradient of g. That gives me this Lagrange multiplier equation. I can solve for lambda, and I get this over that is equal to that over that, which, you notice some things cancel, like the exponentials cancel, and it leaves you with this, which solves to give you x cubed equal, y cubed equal to x cubed. And then, of course, if you plug that into this, that's pretty easy. 2x cubed equal to 16, which tells me x is equal to the cube root of 8, which is 2. And so, likewise, y is 2. And so I get f of 2 is equal to e to the 4. That is apparently my global maximum. Now, how do I know it's the global maximum? I don't know that from these equations. I know that from just like analysis. This is the graph, right? So over here, x and y, one is positive, one is negative. Down here, x and y, one is positive, one is negative. So you're looking at e to a negative number, which is at most 1. So as you go way on out there, e to the xy goes to 0. As you go on down there, e to the xy goes to 0. So e to the 4 is the biggest the function ever gets, and it happens right there, which you probably could have guessed just without calculus anyway, right? Honestly, if you really just are willing to make a guess and to think about things, you probably could have solved this without calculus. I know I'm not supposed to say that, right? Calculus is needed for everything. But if you take a step back and think about things sometimes, you'll realize you can do some things without calculus. Now this one here, we have a function of x, y, z. I'm finding the extreme values of f on the surface. So this is an ellipsoid. And so this one, see the difference between this problem and the last is that, well, we have a one-dimensional constraint, right? So in this case, we just have the gradient of f times lambda times gradient of g, which then gives me these Lagrange multiplier equations. I looked at these and I thought, well, how can I make these all look the same? If I'm solving a system of equations, I like to make them look the same so I can like cancel things. So for this one, it just struck me, I need to multiply them by different Cartesian variables so that they all have x, y, z in them. See, because if I make them all have x, y, z, then I can make all of these have, I can make these all look like x, y, z, right? Multiply this one by x, multiply that one by y, multiply this one by z, then I've got x, y, z, x, y, z, x, y, z, which then I could equate. I get then 2 lambda x squared equals to 4 lambda y squared equals to 6 lambda z squared, which then, of course, gives me x squared equals 2y squared equals 3z squared, which I can then shove into the constraint equation up here, and that gives me 3x squared equal to 6, which then tells me x is equal to plus or minus root 2, And then I have to go back and solve the other ones, which gives me y is plus or minus root 1, and z is plus or minus root 2 over 3, working back in there. All right. This problem we could work out carefully in class in about 15 minutes or so, okay? This one's not bad. Now this is the outcome. We found plus or minus x, y, z coordinates, and the pluses and minuses are not connected, so if you count, that's 2 to the 3, which is 8 possibilities. These are the 8 possibilities: plus, 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 minus, plus, minus, plus, plus, minus, minus, plus, 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 minus, plus, minus, 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 plus, minus, 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 in no particular order. I mean, that's just how I listed them, right? Now, as you can see, you either get what? 2 over root 3 or minus 2 over root 3. So the maximum is 2 over root 3, the minimum is minus 2 over root 3. The reason that these have to exist for this problem, the reason that Lagrange multiplier method is both necessary and sufficient here, is that our constraint surface, this ellipsoid, is compact. So since it's compact, we know by the extreme value theorem we're going to be able to find a minimum and a maximum of the xyz function. Now you might wonder, well, what do level surfaces of our constraint function xyz look like here? Well, they're kind of funky. They're these kind of like hyperboloid sheet. I don't know what these things are called, but they're these curved sheets, and there's one of them in each one of the octants in 3 dimensions. And these 4, there are 8 octants. 4 of the octants corresponds to maximums, and the other 4 correspond to minimums. And I'm not saying that I'm pointing at the maximums and the minimums when I'm putting my mark. I don't know which is which. I probably say up here. Do I? Or am I carefully cagey not to say which one's which in my language up here? I don't know. You can figure it out. There's numbers on them. They're graphs. You could figure it out. Kind of not the point. Here's another closest point to the plane problem. We've talked about that already. There's a useless picture that I don't even know why. If you spent money to print that picture out, my apologies. Here, look, an honest to goodness applied problem. Check it out. You have a rectangular box without a lid, is made from 12 square feet of cardboard. Find the maximum volume of such a box. So what I do, I let x, y, z be lengths of the sides of the box. That means x, y, z is the volume. What's the constraint? Seems like I'm being too tingy with my s's. So since let's see, the 2xz plus 2yz plus xy, that would be the cardboard. Do you see why? Why would that be the formula for the area of the cardboard used? There's no lid, right? So if this is x, this is y, and this is z, you've got xy on the bottom, right? And you've got like zy here, zy there, xz here, and xz back there. So you have 2 of the front, 2 of the sides, 1 of the bottom. That's the formula right there for the area the cardboard used. And then what do? Well, Lagrange multipliers. And then I solve the equations. And you could guess the answer already. Without looking at the calculus, what should the answer be? To maximize the volume using a fixed amount of cardboard with an open top box, what must the answer be without calculus? What's that? They're all 4? No. Right track, though. There is an asymmetry between the role of z and the role of x and y. Z is different from x and y because it's open top. If it was closed top, you'd be exactly right. It would be a cube that's the answer. Because in that situation, x, y, and z would be completely symmetric in their role in the problem. So there can't be an answer that's different than having x and y and z equal. Like if the problem statement has a complete symmetry between x, y, and z, the answer can't violate that symmetry. This is like a general principle. Here, there's a complete symmetry between x and y in the problem statement. So the answer has to have x equals to y which forces you to have like a square bottom. And once you know that, I think you can figure out what z is from there. Maybe? I'm not sure that's true. But anyway, the answer is with x equals to y. So you get 2 by 2 by 2 by 2 by 1, as it turns out. So 4 cubic feet is the magic maximum volume. All right, let's go on here. Here's yet another example. I probably have more examples of Lagrange multipliers than we really need. You can look at my examples if you want, but you should have by now figured out how we set them up, and that most of the trouble is what? Not the setup. What's the trouble? Is the trouble the setup? It is not. The trouble is what? The trouble is the algebra, right? The algebra is the problem, the hard part. So I set gradient of f equal to gradient of g here. This time my objective function is xy, and I'm maximizing out an ellipse. Well, an ellipse is compact, right? It's closed and bounded. So I know an answer exists. I'm going to find maxes and mins here if I can hack through the algebra. And well, the gradient is yx, so I set it equal to lambda times the gradient of g, which gives me these equations, which solve to give me that, which then you can plug back in, and I get either y equal to 0 or lambda's plus or minus 2. If y equals to 0, that doesn't work because then that would force me to also have x equal to 0 according to the Lagrange multiplier equations, but 0, 0 is not on the ellipse. On the other hand, if lambda is 2, then I get solutions. If lambda is equal to minus 2, I get other solutions. So I get 4 solutions, namely 2, 1, minus 2, 1, 2, minus 1, and minus 2, minus 1. So I think 2 of those are maxes, 2 of those are mins. And here's the picture of why that happened. All right. Because if you look at the ellipse and you look at the level curves of xy, level curves of xy are the reciprocal function, right? They're the hyperbolas rotated 45 degrees. And it just so happens that they line up with the ellipsoid, like here and there, as it happens. And I'm searching somewhere in here. I should actually calculate the value of the xy function. I guess we could figure it out. What's the value of the xy function here? X times y is 2 times 1, which is 2. X times y is minus 2 times minus 1, which is 2. So we have a maximum here, and we have the minimum there and there. And that's it. All right, so that brings me to something that's a little bit technical, but I won't go through all the details. I just want to kind of explain to you what the next 2 pages or so of my notes mean, all right? So what I do is I look at the objective function q of xy equal to ax squared plus 2bxy plus cy squared, all right? And here a, b, and c are constants, okay? Not all 0. So a, b, and c are constants, not all 0. This is what's called a quadratic form because it's quadratic, and that's kind of the arbitrary form a quadratic can take if it's all of like degree 2, which is what we're interested in for this problem. And I just want to analyze where is this maximized and minimized on the circle of radius r centered at the origin. And so how do I solve that problem? Lagrange multipliers, right? So Lagrange multipliers, I take the gradient of my objective function, which is q, here it is, and the gradient of the constraint circle function right there is there. And this gives me that ax plus by is lambda x and bx plus cy is lambda y. I solve these simultaneously, and I must solve this, and of course the circle equation all at once. So again, let me not spend too much time on this, just to tell you how it goes. I get a matrix equation. I can multiply by the inverse matrix to solve this. And if I do, I get the x equals to 0, y equals to 0. I get the x equals to 0, y equals to 0 equation. Is 0, 0 on the circle, though? Is 0 on x squared plus y squared equals to r squared? And if r is positive, definitely not, right? So what does that mean? If the inverse matrix forces me to have the zero solution, what must it be the case? It must be that that matrix is one which cannot be inverted. All right? So when you guys take Math 221, what you'll learn is that for a matrix not to be inverted, we must have the condition that the determinant of the matrix is 0. All right? And the determinant of this matrix is exactly what appears in the denominator here, namely this quadratic, which you can rewrite as lambda squared minus a plus c lambda plus ac minus b squared equal to 0. This must be true. It has to be that this is true, because otherwise the matrix would be invertible and we wouldn't get a solution. But we know a solution exists because of the extreme value theorem. So it forces me to say lambda must be this value, plus or minus, right? And then I prove that, well, I don't prove it, but yeah.
How did you reach the conclusion that because I think if I'm following, because the matrix is inconsistent, it's not invertible?
No, if there's either two cases, either matrix is invertible or it's not. In linear algebra, we prove that the invertible matrix has determinant non-zero, and the non-invertible matrix has determinant 0. But this matrix cannot be invertible, because if it was invertible, it would force only the 0 solution for the Lagrange multiplier equations. But we know there can't just be the 0 solution, because it's not even a solution. So now if you rewrite this, it turns out that that can be rewritten as a minus c squared plus 4b squared. The thing about this is it's manifestly non-negative, which means that these lambdas are existing and they're real. All right? So these are real lambdas, which means we can find them. And so, continuing here, there are different cases. If you have b equals to 0, you get these three cases. If b is not equal to 0, you get what's down here. All right? And you work through it. I won't belabor it too much more here. But something really cool happens when you actually solve the problem and plug it in. The minimums and the maximums actually for the quadratic form on the circle are exactly lambda times r squared, as it happens, which is kind of cool. And just to summarize, I have a summary down here of what happens. Now, if you have a quadratic form on a circle, then if you solve the characteristic equation, which is this thing right here, you only have real solutions, and the extreme values for the quadratic form are simply given by lambda r squared, where lambda is a solution to the equation right here. So there are different choices, right? If lambda 1 is equal to lambda 2, it turns out that the quadratic form is constant on the circle. If lambda 1 is not equal to lambda 2, and that's supposed to be a less than, something happened in my, it's a long story, that's a less than. So if lambda 1 is not equal to lambda 2 and lambda 1 is less than lambda 2, the minimum is given by lambda 1 r squared and the maximum is given by lambda 2 r squared. So like there are two different lambdas. The small one's the minimum times r, small one times r squared is the minimum. The big one times r squared is the maximum. And let's see here. So here's just a summary. We can also think about, once we've got that analysis, we can easily think about what would the graph of z, if we think about, the next step to kind of think about here is what would z equals to the quadratic look like, all right? I'm going to reference this discussion like tomorrow, so this is why I have to do it right now. But so like z equals to q of xy, well that, we've studied this, right? If we have a equals to 1 and c equals to 1 and b equals to 0, then we have like z equals x squared plus y squared. You guys remember what that was? Z equals x squared plus y squared. Remember, it was that was the paraboloid, right? It's kind of like the open up bowl that opens upward, kind of. But it turns out that you can understand what the graph looks like if you think about different cases. If both of the lambdas are positive, then that means that the q of 0, 0 is a minimum value for q, and the graph is like a paraboloid which opens up. If the product of the lambdas is less than 0, then the q of 0 is a maximum value. It's like a paraboloid that opens down. As if they're both negative, right? I should say. Now, if one is positive and one is negative, then z equals to q of xy is actually a hyperbolic paraboloid, which means that the origin is what's called a saddle point. It's neither minimum or maximum because depending on which way you go away from z equals to the origin, and z equals q of xy, you'd have a max or a min. And then finally, if one of the lambdas is 0, you get like a parabolic trough when you look at it's all good. I'll fix it. Excuse me. All right. So anyway, we should keep this in mind. We'll have to use this to fully understand something tomorrow. Now, or maybe at the end of today if I play my cards right, I guess, but probably not. It turns out this thing I just did, it has a generalization to n variables. You can read this to properly understand it. Maybe the end of Math 221 you might get to it. Maybe not. But that's that. All right, so that is pretty much all I have to say about Lagrange multipliers. So now I'm going to give you a brief, but hopefully helpful, review of power series. All right. Now, I'm not sure this belongs, I mean, in terms of organization, we could put this a little bit later. I mean, this doesn't have to go right here, logically speaking, but I think it's helpful if I do it here. So, so next topic, I want to talk about multivariate power series. All right. So before I talk about multivariate power series, I probably would be wise to review single variable power series, right? I know there's some demand for this, and I think that's reasonable. I made a handout for you guys. So here is a page that has pretty much everything that you need to know, and then some, about single variable power series. Now what you won't see on this page is anything about convergence or divergence practically, because we don't really care about all that. What we care about is power series computation. In particular, we want to know how to use the, we want to know how to use the Maclaurin series for sine, for cosine, so forth, and then also the geometric series, and then there's a few other tricks we can use to generate new examples from old. Is there an extra one sitting around some? Woohoo! Because I need to look at it. Remember what I wrote you. So the first thing, of course, is that Taylor's theorem says this, right? F of x is the sum n equals 0 to infinity of like the nth derivative at a over n factorial times x minus a, right? So this is the Taylor series centered at a for the function. And so if you don't know the power series for a function, if you can differentiate it, you can generate it through differentiation, right? But this is very, very slow and almost always the wrong way to generate the power series. More typical example would be like this. Let me just do one. So suppose we want to find the power series for, I don't know, x cubed times e to the x minus 1. I suppose I want to find the power series for this centered where? Let's center it at 0 for the sake of discussion to start with. So find the power series centered at 0. What should I do? So I should resist the urge. First of all, I must fight every fiber of my being that says, oh, well, you wrote this here, so you should just start differentiating this, right? No. Thou shalt not differentiate this and apply Taylor's theorem directly. That would be utter foolishness. Instead, we should just make a substitution and use a little bit of algebra. So here this is x cubed e to the x times e to the minus 1 by laws of exponents, right? And then I can just use my known Maclaurin series, which is that is 1 plus x plus 1/2 x squared plus dot dot dot. I'll just stop there for the purposes of our discussion here. And then what's the power series? Well, multiply through, right? So I've got, I'll bring the e to the minus 1 out front, but I got myself an x cubed plus x to the 4th, plus 1/2 x to the 5th, plus dot 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 dot. There it is. That is how I would highly recommend you find the power series for that function. Now, just can you guys tell me some things that you can see about the second or first derivative? What can you tell me about the derivatives of the function just from this expression now? Like if I was to ask you, what is f of 0? What is f prime of 0? What is f prime prime of 0? What are those equal to? Now, why do you say that?
Because the x and x squared terms don't vary.
Right, because there's, yeah, like, because there's no, so like if we look at this, this is f of a, right? Plus f prime of a times x minus a plus 1/2 f prime prime of a times x minus a squared, right? And as you can see, those terms are absent, therefore they must be 0, which is how I can see, how Sam could see that these were all 0 because there is no constant x or x squared term there, right? And a power series is uniquely determined by its coefficients. So you guys, here's one that's non-trivial. What would f prime 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 of 0 be equal to? Let me help you out. What would that over 3 factorial be equal to?
E to the negative 1.
There we go, e to the negative 1. So that tells me that, in fact, the third derivative at 0 would be equal to 6 over e. Or I could tell you that the fifth derivative at 0 would be equal to, apparently, 5 factorial times e to the minus 1 over 2, or 60 over e if you prefer, whatever. I can see that from looking at this and saying, aha, well the coefficient of x to the 5th is e to the minus 1 over 2, but that's equal to 1 over 5 factorial times the fifth derivative evaluated to 0 by Taylor's theorem. There's two things really that go on here. The one is constructing a series by some sort of like sneaky substitution, right? And the other is understanding what the coefficients mean in terms of derivatives. That continues to be interesting for the multivariate power series, as we'll see. Another example, suppose I had y cubed over 1 minus y squared. I wanted to find a power series for this. What would I do? And I suppose I'm still looking for the Maclaurin series, the one centered at 0, just to keep things relatively simple. Yeah, I should think this is a geometric series, right? I can see this from the geometric series. So geometric series says that this is like the sum, of c times r to the n equals 0 to infinity. But here I'm thinking c is equal to y cubed, and r is equal to y squared. And so let's see here. That would actually give me sum n equals 0 to infinity of like y cubed times r times y squared to the n. In other words, we'd have the sum n equals 0 to infinity. I'll get away here in a second. Y to the 2n plus 3. Or explicitly, you got like yourself a y cubed plus a y to the 5th plus a y to the 7th. Yeah, plus dot 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 dot. there's the power series centered at 0 for this function. I did not differentiate anything, did I? No. Substitution is definitely the way to go here, okay? So I'll just take a breath here. Do you guys have any questions about power series now you've got the sheet in front of you? Do you want me to work a few more examples before I go back to the multivariate thing? Should I do one not centered at 0 maybe? Let's try that, yeah. What if I wanted, let us suppose, to find let's say we're looking at f of x equals to, let's say, e to the minus x times the cosine of x, and let's find power series centered at, you know, a equals to, let's say, pi over 2 to order, let's say 6 for giggles. I'm probably going to regret that. So what that means is I'm trying to expand things in the form x minus pi over 2. Right? This is what I want. I want powers of x minus pi over 2. So to make that happen, I basically need to, we'll add 0 is probably the easiest way to do it here. Now, of course, you could just differentiate 6 times. It wouldn't take that long. Then you evaluate at pi over 2 and use Taylor's theorem. That's one way, right? It's not impossible. You could do it that way. But I like to do what I'm about to show you, which is e to the minus, so I've got x minus pi over 2, right, plus pi over 2, and then cosine of x minus pi over 2 plus pi over 2. So I just add 0 to make the kind of, yep.
What you have to do, since that's inside the negative, what you have to do minus pi over 2 and another minus pi over 2, because that negative cancels out. You can end up adding.
Oh yeah, thank you. Thank you. Yep. Okay, so then algebra, right? I got e to the minus pi over 2 out front, and then I've got e to the minus parentheses x minus pi over 2. And how does that simplify? Well, that gives me a, that just gives me sine of x minus pi over 2, right? Can you guys see why that is? Let me remind you, this right here, right, would be cosine of x minus pi over 2, cosine pi over 2, minus, I may have missed a sign, right? Sine of x minus pi over 2, sine of pi over 2. As you can see, I'm not quite right. What have I missed? What's sine of pi over 2? You shouldn't need a calculator for this. You should know sine of pi over 2 is 1. You should know cosine of pi over 2 is 0. If you don't know that, you're wasting your time on tests. Seriously. Like every time you have to pick up a calculator to look that up, you just lost like 20 seconds. I know it seems like a small thing, but these things add up. On the other hand, if you're not sure, by all means check, you know? But anyway, so the first term is 0. The second term, as you can see, generates a minus, right? So I owe you guys a minus out here. And then what? Okay, now we're to standard functions, exponential and sine, and we can just go to the sheet basically and make a substitution. Think about u equals to x minus, you know, like think about putting u in here in the formula, setting these things equal to u. And so what I have is a minus e to the minus pi over 2, I'll leave that out front. And this one gives me 1 minus x minus pi over 2. I really regret that, order 6 at the moment. Plus 1/2 x minus pi over 2. I think I'm going to have to erase that 6 squared because there's a lot here. Let's maybe order 4 maybe would be not so annoying. Let's see here. I may still regret that. 1/6 x minus pi over 2 cubed plus 1 over 24. 24 is 4 factorial, right? X minus pi over 2 to the 4th power plus dot 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 dot. So what have I done so far? That's just the expansion for the exponential, right? And then what do I have? Now I've got the sign up next, so that's x minus pi over 2 minus 1/6 x minus pi over 2 cubed, right? And then the next term up is what? Order, yeah?
Wouldn't it oscillate between negative and positive?
Oh yeah, did I? Oh, but, okay, but that is oscillating because, oh, this one over here, did I miss a minus? I did minus plus, oh, thank you. That was supposed to be minus plus, okay. I was oscillating, I missed one. Thank you, helpful, very helpful. Now over here, this is the plus, then that's the minus. The next is order 5, so, you know, we can drop that. I think the smart thing to do in this problem is to resist the urge to stay in this notation. Okay? Like, it would have been very helpful if instead of using x minus pi over 2, even at the last step, I'd done what? What would be computationally very helpful here is to use a different letter in like a shorthand for all this, right? So, I mean, we could just do this is minus e to the minus pi over 2 times 1 minus u plus 1/2 u squared minus 1/6 u cubed plus 1 over 24 u to the 4th plus dot 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 times u minus 1/6 u cubed. See, that's, I think we're much less likely to make a mistake if we use that notation at this step. Because now, what do I have to do to find the power series? Just algebra, right? So, minus e to the minus pi over 2. What do we got? What's the lowest order thing here, multiplying it out? Is there a constant term? No, because the u over there messes it up, right? But this 1 times that u gives me a u. Is there any other constant term? No, see, because then this u times that u gives me a quadratic. So that's it for the up to first order. What's second order then? How about this one? Does it have hit anything over here? No. The first thing that produces past linear is cubic. So I have so I get minus u squared. This times that gives me that. I think that's it for second order, right? How about third order? How can we get third order terms? Maybe that's more interesting. We get this times this, right? So we get a minus 1/6 u cubed. And then what else can we get? This gives me a fourth order term. I don't care about that yet. I go order by order, okay? I'm looking for everything cubic. Oh, but this is plus 1/2 u squared. I think that cubed rather. That's it for third order. Like everything past that's quartic or higher. How can I get fourth order? Well, this 1 never produces fourth order, right? But minus u times that gives me a plus 1/6 u to the 4. How else can I get fourth order? Well, the u squared doesn't produce anything of interest because that, you know, either gives me a cube or a 5 at lowest order. But the cube here, I get what? Minus 1/6 u to the 4. Is there any other u to the 4th going on? I think that's it, right? So it looks to me, if I haven't made a mistake, right, that we have minus e to the minus pi over 2 times, well, let's see here, x minus pi over 2 minus parentheses x minus pi over 2 squared. What's 1/2 minus 1/6? 1/3, right? So 1/3 x minus pi over 2 cubed, and then that's it. To fourth order, I believe that's the power series expansion of this function. So obviously that that example is a little bit tougher than my first one, right? But these are some of the strategies that you can use. Now, you can ask in retrospect, was this worth it, or would it have been easier to just differentiate this 4 times and evaluate? I mean, it's debatable, right? For some of you, if you're really good at differentiation, maybe differentiating 4 times and applying Taylor's theorem would have been faster. I don't know. So anyway, any questions? No?
To do this with the sum notation, you have to use a Cauchy product.
Well, that's what I'm doing. The Cauchy product is exactly what I'm doing. I'm gathering together all of the terms which give me linear, all the terms which give me quadratic. Like I'm grouping them order by order. That's the Cauchy product. Yeah. That is what's going on here. Okay, so let me, now that we've had a brief walk down memory lane, how does the multivariate power series go exactly? What is the multivariate power series precisely? So, man. So we could derive it. I don't usually derive it in here though. So it's just a little bit beyond the edge of where most Calc 3 books get to, which is unfortunate. I was in grad school, and I discovered that there was a multivariate power series when I needed it for a problem I couldn't solve. I was like, what? I have read every stupid page in Stewart. It's nowhere in there, you know? And so I was pretty annoyed that I had spent a long, long time on Calculus 3 as an undergraduate, but it didn't matter how long I spent because the book I was using refused to even discuss this topic, which is actually kind of important topic because it's a major tool of multivariate analysis, this idea of multivariate power series. And it's not that hard either. Like, here's the result. The result is simply this. If we have a function of n variables, I'll just write it in kind of like a vector notation. F of vector x, which you can write is simply this. The sum n equals 0 to infinity of like, and this is going to be ugly, I1 equals 1 to n. Oh man, bummer. I got to make that a k. I2 equals 1 to n. I sub k equals 1 to n of, I think, I got to check myself on the factor here. Yeah, it's just k factorial. There's various ways to write this formula, so I got to, all right, so 1 over k factorial, and what we're looking at is the kth derivative of f, partial xi1, partial xi2, partial xin. This gets evaluated at, let's say, a, and then you've got like xi1 minus ai1, xi2 minus ai2, xin minus ain. I don't think I put this in the notes, guys. And you might see why I didn't. It's kind of ugly. But that's it. That's like the multivariate. This is just for a function from Rn to R. This is what the multivariate Taylor theorem looks like. Now, let me just write out like the first 3 terms of this, okay? So in particular, this looks like f of a, all right, plus, and what this becomes is just the sum I equals